Hello, everybody. This is Carol speaking. Welcome to our PolyWorks webinar. Just a little heads up, this is our last webinar before we go on a short break. And I hope you're going to be enjoying it. And we're talking about how to avoid costly CNC CMM equipment damage. And let's welcome Roberto Barreto, as he is our presenter today. Roberto is a member of the technical support group. He is making his debut as a webinar presenter, but definitely not as a presenter. He's made several presentations you may have seen him during our conferences. And let me remind you that if you have any questions during the webinar, please use the questions panel. I will be monitoring the questions throughout the webinar. And as usual, we will have a Q&A session at the end. If you don't have time to answer all of the questions, we'll get back to you by email. And yes, we are recording this webinar, so it will be available for later viewing. So Roberto, it's all yours.
Thank you, Carol. During the creation of CNC CMM measurement sequences, our goal is to define collision-free measurement paths as quickly and as efficiently as possible. Doing so not only reduces the amount of troubleshooting needed before our sequence is ready to run, but it also helps us avoid costly equipment damage. This webinar will present the different tools available in PolyWorks to detect, analyze, and avoid potential collisions while preparing sequences offline or online. Here we have a simple project in which we have already defined all of our measurement objects and in which we have created a draft measurement sequence that starts by measuring the objects needed for the alignment of my part. I'll start by executing some of the steps on that sequence, which will be the measurement of 2 circles and 2 comparison points on the top face of my part. By activating collision detection, our sequence is analyzed in real time, and we get an indication of the sequence steps for which a potential collision could occur. If we look at the pad for the first step, it's quite obvious what the issue is, since the pad is going across the CAD model, causing a potential collision. In addition to detecting potential collisions, the sequence editor offers fixers that can help us solve the potential issues. In this case, inserting a go-to position step between my circle and my comparison point will solve this particular problem. The next collision occurs right after the probing of my surface point 3 when going back and probing circle 3, which is on the top face. And we see it's a very similar issue than the one we had before, since we're sending the probe back to the top face right after probing point 3, and we still have a collision with the pad and the CAD model. Now, to fix this, I could try to simply add another go-to position as we did before. But if you think about it, it makes more sense to simply probe that hole while my probe is still on that top surface of the part. So what I can do instead is reorder my objects, basically moving circle 3 right after the probing of circle 2. And by doing so, our real-time collision detection engine will update and it will clear the potential issues that were there for the probing of those objects. I'll quickly execute those steps now so that we can probe the circle, the comparison point on the bottom using the go-to position point, and now we'll have an active alignment. The next detected collision is for the measurement of surface point 6. And if we look at its pad, it is not so obvious what the issue might be and where the collision might take place. So in order to investigate further, we can use a different fixer from our sequence editor, this time to analyze the potential collision. This will temporarily position the machine where the collision would occur on that particular step. This mode also helps us understand how collision detection works. First, we see that even though the pad is clear and there's no potential collisions between the pad and the CAD model, if we look a little bit closer, we'll see that there's potential collisions with some components of my tool and the CAD model. This is why collision detection not only considers the measurement paths, but everything from the probe tip all the way to the quill of the machine. In addition to that, we see a bounding box surrounding each one of the components of my tool. This is because a safety factor is used in order to detect potential collisions with the part. This will account, as I was saying, for potential deviations between the real part that can be deviated by 1 or 2 millimeters depending on your application. Or it can also be there to account for potential differences between the reference objects imported into PolyWorks and the real objects. The safety factor is found in the PolyWorks inspector options, and it needs to be modified based on the expected deviations of each application. Modifying the value will adjust the bounding boxes in the 3D scene to reflect the newly selected value and adjust and detect collisions using those new bounding boxes. While still in the path analysis mode, we can quickly move to the next steps in my sequence. And we will see that the issue was not just with 0.6, but as we move further right along the measurement of the trim contour, the collisions become more obvious between my tool and this portion of my CAD model. So to fix this, one potential thing that we could do is simply using a different tool orientation, which would make it so that my probe head will be a little bit farther in this direction and we can probe still those points with the tool without causing any collisions. I'll do that right away. I'll go back to our sequence creation mode and start our recording. And with the help of our fixer, we can go ahead and pick the desired tool orientation. Doing so, however, immediately flags a collision since we're too close to the part to perform that tool orientation change. This would have also prevented a collision if we were trying to do this while being connected to the machine and working online. To prevent this from happening, I can insert a go-to position that will send the probe to a safe height before changing the tool orientation. And then using our tool orientation picker to choose the right orientation. Since we're in recording, both steps will get added to my sequence, and we'll see that most potential collisions from my trim points are gone. However, some still remain. The first one is found for surface point 7, and it's found right after the probing of point 6 when going across the clamp. This one we can simply fix the same way we did initially by inserting a go-to position in between those 2 points. The software will automatically compute and find 2 safe positions that will allow me to clear that potential collision. However, if we look at the next one, which is on the other side of the clamp, it is once again not so obvious what the issue might be. So once again, we can go back to analyze that potential collision. And we'll see here that the issue is that we have a part of our tool that might be in collision with the clamp that's located there. Now, that clamp is very close to the point we're trying to measure, and one potential solution to this is simply using a different tool orientation that will allow me to probe that point without colliding with the clamp. However, let's say that after discussion with colleagues, it was decided that removing the clamp from the fixture is an acceptable solution. By deleting the elements that belong to the clamp, our real-time collision detection will update, and you will see that I will no longer have any potential collisions in my sequence. At this point, however, if we look back at the steps that we had there, we had added 2 go-to positions to avoid that clamp. So what we could do is optimize our go-to positions, which is a tool that works on a selection of steps, and it will either reposition the go-to positions based on the new changes, or simply remove them if they're no longer needed, which is the case right here. We have seen in this project that having the CAD model of my fixture allows me to detect potential collisions with it. But what if we don't have a CAD model for our fixture? One possibility is to scan our fixture using real-time quality meshing, and then using the resulting polygonal model, as a reference object for collision detection. In my current project, it will look something like this. And you will even see that because my clamp is now back, my collision detection engine has now brought back some of the collisions that we had there before. I have prepared a second example in which we have a complete project with a collision-free measurement sequence. It uses 3 tooling balls to align to the part, and it then measures the trim contour of this sheet metal part. The challenge is that to measure this part, it needs to be fixtured using several clamps that might cause collisions. And this, of course, needs to be taken into account before being able to run this program in our CMM. That is why we took the time in a second project to scan my fixture using a portable arm. Note that since PolyWorks is a universal platform, any 3D scanning device can be used, even an old arm or an old fringe projector that you might have, since the scan does not need to be perfect, just close enough to be able to detect if the bounding boxes that we saw earlier will collide with any of the scan triangles. In this case, I scanned the fixture with the part already in it to make sure the clamps are in the same position they will be in when performing the CNC CMM inspection. Before I'm able to use the scan, however, I need to make sure it's aligned to the CAD model of my inspection project. So I will begin by importing that CAD into this project. And in this case, because we scan the part as well as the fixture, a simple best fit data to reference alignment should be enough to align my scan to the CAD model of the part. In this particular scenario, it is probably a good idea to remove these points that would scan on the part itself to prevent collisions being detected with it, especially since we already have the CAD model of the part for that purpose. An efficient way of doing this is to log your alignment from the properties, and then using our advanced selection tools to select all of the data points that are close to the CAD model. Alternatively, if your fixture has tooling balls or any other reference geometry, you could align your scan to the CAD using them instead. This can be a very efficient way of aligning your scan, and also very helpful if scanning the fixture with the part already installed is not possible or it's difficult. In this example, in addition to scanning my fixture, I probed the 3 tooling balls that were in it using my portable arm. And at this point, I can define the nominal location of those spheres numerically by using either the coordinates that were printed on the actual fixture, or even by the coordinates that I could obtain by probing the same points using my CNC CMM. In this particular project, I already defined the nominal location of my other 2 tooling spheres. So at this point, I can align my scan using a best fit measurement objects alignment that uses the 3 spheres. At this point, I can simply save my project and return to our inspection project to import that scan into it. As expected, it is already aligned, so the final step I'll have to do for it to be considered for collision detection is to convert my scan into a reference object. From this point on, we can troubleshoot all potential collisions like we did initially during the first part of the webinar. Or we could even simply select the steps where collisions are included and optimize the go-to positions, which would even not only optimize the existing ones, but find additional go-tos that will help us avoid the collisions in this particular scenario and give us a collision-free sequence.
Thank you, Roberto. So we have some questions that are coming in. And the first one is regarding the scan of that fixture. So how complete must the scan be of that fixture in order to use it as a reference like you just did?
So in this particular example, you will see that it is not a perfect scan, not even close. You'll see that I didn't even scan perfectly all of the clamps. There's holes in many of the areas, so you don't need any watertight scan. It needs to be, you can even just focus on the areas that you know might cause potential collisions. So it's, I mean, you'll, depending on how many times you'll be using that fixture, you'll try to do more detailed work of scanning or not, but this is a quick scan that we did, and it's enough to know where the clamps is. And remember, there's always a safety factor being used. So even if your scan is not either fully complete or fully accurate, it will still be more than enough for us to be able to create collision-free paths.
Okay, thank you. And second question is a little bit along those same lines. What about the CMM table? This has to be scanned. We consider it for a collision?
Yes, so you don't have to scan your CMM table because it is already defined in your CMM configuration. So we know where the table is, and it will be considered for collision. So if you were, for example, connected to your machine and you were just changing tool orientations or even doing a project, if eventually a collision would occur with the table, it will be detected by our collision detection engine.
Okay, and one more question. Is it possible to disregard or to ignore some reference objects for the collision detection, but still use them for other things?
It is a good question. One thing you could do is, as I was doing in my initial project, we can ignore an object while we're building the measurement pad. But then if it is used, it will still be used for, I think it's a good request. For now, the way to do it will be to, while you're working with the collision detection on, you can ignore the CADs that you don't want to detect collisions with. And then once you do have your measurement, your collision-free path, then you can safely bring it back and it will work.
Thank you. And this is all the time that we have for the questions. So this webinar has been recorded. It will be available on the Innovmetric software website. Navigate to the support section. It will also be available on the Innovmetric software channel on YouTube. So our next webinar, well, like I said previously, this was our last webinar before we go on a short break, but we will be back February 14th, so mark your calendars. As for the topics, well, you have to stay tuned. It will be announced on our website. Thank you for joining us this morning. And on behalf of the Innovmetric team, we wish you happy holidays, be safe, and we'll see you in 2019. Bye-bye, everybody.